Hi everyone and welcome back to the channel. In today's video, we'll be going through a thorough review of the mechanical design and analysis section relating to the FE mechanical exam. This review will be especially helpful because we'll cover the most important and frequently tested topics in this section, and we'll not only break down key concepts, but we'll also walk through example problems to reinforce your understanding and ensure that you're prepared for exam day. The mechanical design and analysis section is a pretty large portion of the FE mechanical exam. You can see it's 10 to 15 questions over here. And because of that, it's a high impact area and a good place to focus in your efforts on to maximize your chances of passing. Now, this section in particular pulls together a lot of foundational concepts from statics and mechanics of material, things like Hooke's law, Moore's circle, stresses and stress distributions, beam deflections. Mastering those core concepts will make studying for this section significantly easier, as much of the mechanical design section focuses on those principles. Now, here's how I set up this review. We'll cover the most important mechanical design concepts by working through 12 different example problems that I've carefully selected here, with timestamps in the description so you can jump around if you want to focus on specific topics here. The left-hand side in the specification here, it focuses on the amount of times in the review that we touch that specific subtopic, just to give you an idea of coverage. Some of the specific topics that we're going to cover inside of the review include the max shear stress theory of failure. We'll go through helical compression springs, bearings, power screws, bolt grooves with eccentric loading, hydraulics. We'll talk about spur gears and gear trains, bolted joints. We'll talk about important concepts like preload, the joint coefficient, and we'll go through the joint diagram for more conceptual understanding on bolted joints. We'll look at pressure vessels, quality and reliability, and we'll touch a little bit on GD&T, specifically a concept called max material condition. On the right-hand side, you'll see a subset of schematics from the problems that we're going to solve today, all of which were taken from my educational platform, FE Interactive, and that's the first link in the description below. This review will follow a pretty consistent format. We'll have difficulty tags on the top of the question. So this is a hard question, followed by a diagram. If that question has a diagram, then we'll see the problem statement and answer choices. Most of the questions on the FE exam are going to be multiple choice, so that's going to be our focus here. And on the right-hand side, you can see the exam spec with the specific topic that that question is trying to cover highlighted. You can try all of these problems for yourself using the second link in the description below. Once you click on that, it'll bring you to a screen like this. You can go ahead and click Filter, Mechanical Design and Analysis, and then Collapse. And you can have access to all of the questions that we're going to solve today. You can input an answer choice, view the explanations, typed and handwritten, and then you can watch the video solution. It'll link back to this video. Let's go ahead and get into the review. In this problem here, we have a steel hook and it supports a vertical load at its lowest point. That's this load P depicted on the diagram. The hook has an inside diameter of 8 inches and a solid circular cross-section of 1.5-inch diameter. So if we kind of draw those dimensions on this diagram, we have this dimension uppercase D, I'm going to call it, is equal to 8 inches. And we know that the rod is constructed with a circular cross-section, lowercase d, and that's equal to 1.5 inches. The material has a yield strength, S sub y, and that's going to be equal to 30 ksi. Assuming the critical section occurs at the location of maximum bending, the failure load predicted by the Tresca, also known as the maximum shear stress criteria, is most nearly. All right, so this problem is really focused on stress analysis of machine elements. We have a hook with a static load applied at its lowest point. So that is that section A. And we know that in order to determine the failure load, we're going to be applying a failure criteria for ductile materials here, also known as the Tresca or maximum shear stress criteria. We could alternatively use von Mises, and typically Tresca is considered more conservative, and the problem would be pretty similar if we look at either one of those failure theories. So the first thing I'd like to do is discuss the idea of the Tresca failure criteria. So the statement of Tresca says that failure will occur in a body when the maximum shear stress in that body reaches that at failure in a simple tensile specimen. So to give you some intuition about this failure criteria, what I want to start with is a simple tensile specimen with a load P applied. And if we make a cut right here and observe a stress element, when this tensile specimen is going to fail is when the stress produced at that section is equal to the yield strength of the material. So what we would have is something like this. So we would have a stress element that looks like this, where the stress in that stress element is equal to the yield strength. And if we think about the maximum shear stress in this body, what we would have is, what we could do is draw more circle and think about stress transformations. So we have a sigma in the x direction equal to the yield strength. So this would be S sub y here, and there's no shear. The axes here, if you didn't recall, was the normal stress and shear stress here. So if we plot the state of stress there in the x direction, it's just equal to the yield strength, comma 0. So it just lies along that x-axis. For the stress in the y direction and z direction, both of them are 0, such that Mohr's circle would look like this. And you could see that the radius of Mohr's circle, which physically represents the maximum shear stress, is equal to half of the yield strength at failure. So this is essentially the failure load that we're going to be comparing to. If I repeat that kind of statement of the maximum shear stress criteria, it says that failure will occur in a body when the maximum shear stress in that body reaches that at failure in a simple tensile specimen. At failure for a simple tensile specimen, the failure shear stress is the yield strength over 2. So we're going to compare the maximum shear stress in this body to half of the yield strength. We know that that critical section is going to be occurring at the location of maximum bending, and that's going to occur at the furthest perpendicular distance from that force's line of action, since that's when the distance is the maximum. You maximize the distance, you'll maximize the moments, and what you could see is that the critical section is really this section right here. So we're going to draw the free body diagram after we make that section cut and understand some of the internal loads that exist there that produce the stresses. We're going to use those stresses and transform them to calculate the maximum shear stress, and then we'll be able to compare that to failure in a simple tensile specimen, essentially applying the Tresca failure criteria to find the failure load. So based off of our section of maximum bending, we went ahead and drew the free body diagram here, where we have the externally applied load P, and then we have at the section an internal axial load N, an internal shearing force V, and an internal bending moment M. And we can apply equilibrium to find each of these, the easiest one being the sum of the forces in the horizontal or x direction. That tells us that the internal shearing is equal to 0. We sum the forces in the y direction and set it equal to 0. What we see is that the internal axial load is just equal to the externally applied load P in magnitude. And if we lastly sum the moments, and we're going to do it at the cut section, if we say counterclockwise is positive, set that equal to 0. The concentrated moment is the only one that's going to be producing the moment in terms of our internal loads. N and V, they're at the moment point, so we technically don't get any contributions from those. That must be equal to the moment produced by that externally applied load. That clockwise moment is equal to P multiplied by the distance. And the distance from the kind of center of the cross section. Remember that all of these internal loads go from the centroid of the cross section that we made the cut. So the first thing is that we're going to have to travel a distance of lowercase d over 2, and that's the kind of radial distance that will get us to this kind of inner surface of this hook. And if we go ahead and just put an arrow to where that would make us end up, that would be right here at the inner surface of the hook, and we still have to travel over a distance equal to uppercase D over 2 in order to arrive at that line of action. Okay, so this is what the internal bending moment is equal to. Now, if we think about it, internal loads will produce stresses. And if we think back to the mechanics and material review that I did, if you didn't see that, you could check that out, because a lot of the problems that we're going to be doing in the mechanical design section are a reliance on a good solid foundation in statics, and mechanics of material. So if you didn't check out the mechanics of material review, definitely check it out. We go through some of the fundamentals of that section. One of the topics being this stress summary, right? When you have an internal axial load applied, like this load P right here, it produces a uniform stress in the cross section that's equal to P over A. We know that we have no internal shear, so we won't produce any transverse shear, and there is no moment that is perpendicular to the cross section in this problem. If you curl your fingers in the direction of our moment M, it's into and out of the page, right? So it's technically parallel to the cross section. In order for something to produce torque, its moment vector has to be perpendicular to the cross section. Ours is, curl your thumbs in the direction. You can see that it's into and out of the page. So there's no torsion produced, but there is a bending stress. And that bending stress is going to vary along our cross section. So if we kind of zoom into the hook there, right? And that internal axial load, that's going to produce something uniform, right? And it's going to be tensile in nature. What we're looking for is where the most tension is going to be for our moments. We understand that our moment vector is kind of in this orientation. We draw it on a 2D page here. It's curling in this direction. That would mean that what we have is a tension on the inner diameter. This is kind of the inside of the hook, and this would be the outside. So you can see that if we drew those forces, then it's clear that we would have the most tension on the kind of inner surface of that hook. I'm going to just draw this like this so that we understand. We connect these two in a linear fashion. What we're going to get is the most tension on that inner surface. The magnitude of this maximum tensile stress due to bending, sigma is equal to mc over I, where c is the distance from the neutral axis or the centroid of that cross section to the outer fibers. So that is this lowercase d divided by 2, or we could just define that as a lowercase r, the radial distance. And the moment of inertia for a circular cross section, that's just equal to pi r to the 4th over 4. And after we finish solving the problem, we're going to go through where you can find this information in the reference manual. You can see I have a list here of where you can find some of this information over here, page numbers and section headings. Okay, so in terms of our stress, we're going to have a stress on contribution to that uniaxial stress that we're going to get in this case is equal to P over A, and it's tensile. And then in order to maximize this tensile stress, we're going to want to add the maximum bending tensile stress also, right? So that's going to be equal to MC over I. So I'm going to leave the P over A as is, and I'm going to just make some substitutions for that internal bending moment that we found to be P multiplied by uppercase D plus lowercase d over 2. So we found that from equilibrium over here. The C value is just the radius of that cross section here. And the I value is just pi r to the 4th over 4. And what we could do is rewrite this. I see an area term on the left side, and I see another area term over here, except with some extra contributions. I could just rewrite this as P over A plus P multiplied by uppercase D plus lowercase d over 2 multiplied by the radius. We have a pi r squared contribution. There is an additional divide by 4 there, and there is an 2 r's, right? There's an r squared technically. One of the r's is going to go, and we're going to factor out the rest of the area term here. So we have this stress. We have this stress term here. If we think about what we're really trying to do, we're trying to apply a failure theory looking at the maximum shear stress in the body. Now, we already looked around on the cross section to see where the maximum normal stress is going to occur, because if we think about Mohr circle for this uniaxial case, what we have is a stress element kind of like this, where that stress, let's call it sigma 1. And it's technically a principal stress. It's a stress in the absence of shear. There's no shear on the stress element. So we have this sigma 1 that we can plot over here. That's the stress in the y direction. And the stress in the x and z direction are both considered to be 0. So we get a Mohr circle like this. And we can see that the radius of Mohr circle is just half of that first principal stress. So that is the maximum shear stress for our hook. And we're trying to compare that to the maximum shear stress in a simple tensile specimen. We found that equal to half of the yield strength from above. You can see that these twos are going to cancel out. So failure is going to occur when the first principal stress reaches the yield strength of the material. And we have a expression for the first principal stress here. That's just P over A multiplied by this parentheses term, 1 plus 2, multiplied by uppercase D plus lowercase d divided by the radius. That's equal to the yield strength. And if we solve finally for our load P, if we remember it was 30 KSI, our area, that's just pi times the radius squared, or half of this little d, which was 1.5. So we have a quarter right here. Pi r squared is our area, divided by 1 plus 2 times big D was 8, small d was 1.5, and we're going to divide by the radius. That is technically half of the small d, which is 0.75. We plug this in, is equal to 2.01. And what kind of units do we have? We had the, this term right here was the yield strength measured in kips per square inch, or KSI. The area was measured in square inches, so this is measured in kips. And then the bottom term, you can see that it is dimensionless because look at this 1 right here. You can only add together similar terms. That must mean that whatever you're adding to is dimensionless, or you can check over here, right? The ratio of 2 distances, that's also dimensionless. All right, so what we get is answer choice A, so that is the correct choice. And if we just look inside of the reference manual, I want to explore some of these references that we have here and show you where you can find the information that we used in this problem to solve it. So over here is the FE reference manual on page 95 of the reference manual. This is the static section, and this wasn't in the list of references that I gave you guys, but I'm going to show you guys a quick trick on how to remember the moment of inertias and the polar moment of inertia for a circle. So usually what I do is, I think back to the kind of first principles definition of the polar moment of inertia. In general, is the integral of r squared dA. And this is in general, but for a circle, you can write this differential area as 2 pi r dr. If we go ahead and substitute that in and perform our integration, what we get is pi r to the 4th over 2. Now that's the polar moment of inertia for a circle, and I usually quickly do the derivation just like this in order to get the polar moment of inertia for a circle. And I've done it so many times that I recall the polar moment of inertia. And there's this special property for circles due to symmetry that the moment of inertia in the x and y direction are equal. And they're actually equal to half of the polar moment of inertia. Right? So if you can remember the polar moment of inertia, you cut it in half, you can get the moment of inertia about the x or y axis. That's called the perpendicular axis theorem. I'm sure most of you are familiar with the parallel axis theorem. And really, it's about that symmetry property. That's why this is true. You can see that we have a couple of definitions up here. They wrote the polar moment of inertia in terms of its components. The x squared plus y squared is r squared. The integral of x squared dA right here is defined as the moment of inertia about the y-axis, and the integral of y squared dA is the moment of inertia about the x-axis. So you can see that's going to be equal to j. And because they're equal, double ix or iy is just going to be equal to j. You can cut the j in half if you ever want ix or iy. So that's usually what I do. Now, if you absolutely hate derivations and you don't remember any of that, you can go to page 99 of the FE reference manual here, and you can find the polar moment of inertia of a circle, or the moment of inertia. That's the moment of inertia is what we use for our problem, for our mc over I. So that's where you would find that on page 99 in the static section. Now, let's go ahead to some of the stresses that we were using here. inside of our hook, we had the stresses in the beams. Specifically, we were looking at the max normal stress due to bending, and we use that MC over I term. And we also had the uniaxial case, which is this is on page 136. Now on page 131, you can see for the uniaxial case where we had that P over A that we added to our MC over I. And the last kind of section here was the last section was the section on failure theories. And you see the statement that they wrote on the failure theory, the one that I kept saying in terms of the simple tensile specimen. And this is where you would find that. You see the maximum shear stress is just the yield strength divided by 2. And you can see inside of the body, right, they really look at the principal stresses, sigma 1 minus sigma 3 over 2. And that's technically what we did, right? We just took the difference between sigma 1, which is our largest first principal stress. Sigma 3 is our smallest principal stress, which was 0 for our case. And in that special case where you have just pure uniaxial loading, just sigma 1 and sigma 2 and 3 are 0, then we simply compare the first principal stress to the yield strength for this failure criteria. So it kind of became more simplified in this case. Okay, let's go ahead and move on to the next problem. In this problem here, we have a helical compression spring. It's used in a mechanical assembly and is subject to a compressive force of 120 pounds. So F is 120 pounds here. The spring is made from steel wire with a diameter of 0.2 inches. Let's call that lowercase d equal to 0.2 inches and has an outside diameter. So we'll call that uppercase D outside is equal to 2.25 inches. The free length of the spring, let's just call that L, is equal to 5 inches. And if the yield shear strength for the material is 85 KSI, we're looking for the factor of safety against failure. Okay, so we have a spring here and it's being compressed. So we're going to have some shear stress induced inside of the cross section of that spring. And to quantify that shear stress, there's an equation inside of the FE reference manual. So I'm going to go ahead and go straight to the FE reference manual here. Now, inside of the mechanical design section, mechanical design and analysis section, there is a section on springs, and that is on page 433 of the reference manual. You can see that there is a relationship here between the shear stress and the force that's applied. So lowercase d is considered the wire diameter that was given to us in the problem. We're also given the applied force. We were not given the mean spring diameter, but we were given the outside diameter, and that was equal to, I think it was 2.25 inches. So we can use the outside diameter and the wire diameter to find the mean spring diameter. So we could find that. We need this K sub S term. It's a function of this uppercase C, which is actually referred to as the spring index. And you can see it's dimensionless here. The ratio of the main spring diameter to the wire diameter. And we're going to go ahead and use this equation to solve our problem. All right, so I went ahead and pasted this equation over here. So we know that the shear stress tau is going to be equal to K multiplied by 8 FD divided by pi times the diameter cubed. Okay, so that is the shear stress, and we know that the I put yield strength over here. Technically, it's a yield shear strength. So I'm going to call it tau sub y here. That's equal to 85 KSI. Now, once I take the ratio of the yield strength to the actual shear strength in the body, what I'll get is the factor of safety. So all I really need to do is calculate what that what the shear in the body is. So we understand that we can, using the outside diameter, which is 2.25 inches, we technically have a few different circles, right, that make up a spring. So if we think about a spring here, oh my God, that's terrible. Okay, that's pretty bad too, but I hope you guys are able to understand this. So that spring could technically fit inside of a cylinder, and the cylinder that it would be able to fit inside is equal to the outside. And we do not want the outside, right? For all of these equations, we want the mean diameter. So technically, we would have to subtract off half of the wire diameter on one side and half of the wire diameter on the other side. So what we do to get the mean diameter, uppercase D, is we take the outside diameter and subtract off the wire diameter. We subtract half on one side, half on the other side, and technically we'd be at a kind of mean cylinder for that spring to fit into. So this is the D that we're looking for. We just take 2.25 and subtract off the wire diameter, which is 0.2 inches. So that means our uppercase D is 2.05 inches. Okay, so our K value, that's going to be equal to this equation right up here. And it can be calculated using the spring index, which is dimensionless. So the first thing that we're going to calculate is the dimensionless spring index, C. That's uppercase D over lowercase d, or 2.05 divided by 0.2. So that's equal to 10.25. Now let's go ahead and calculate what K is going to be. K is going to be 2 times 10.25 plus 1 divided by 2c. I'm using this equation that I'm starring right here. And c was 10.25 here. I'll go ahead and plug this in. 1.0488. If I round it, that's a dimensionless term there. So we're going to go ahead and plug it into the shear stress equation. Tau is equal to that K value. The K value was 1.0488 multiplied by 8 times my force. That was 120 pounds. Uppercase D was 2.05. That is our mean diameter divided by pi times 0.2 cubed. If we go ahead and look on the units over here, we have a 120 measured in pounds. That 2.05 was measured in inches, and there's an inch cubed here. So we technically get a result in PSI here. I'm going to multiply by 10 to the minus 3 here so that I get the result in KSI, and the result in KSI is equal to 82.123 KSI. Just go over here and take the ratio of the yield strength and shear, which was equal to 85 KSI, to the actual shear stress in the body, which is 82.123. I get a factor of safety around 1.035. That is this value here, or answer choice A. So let's go ahead and move on to the next problem. In this problem here, we have a ball bearing with a 3/8 inch bore. So that diameter of the inside is 3/8 of an inch. It supports a shaft under a 120-pound radial load and a 40-pound thrust load, or an axial load. So the radial load is 120 pounds, and the thrust load, or the axial load, is 40 pounds. The outer race is fixed, or so we could say the outer race is fixed, or the inner ring is rotating. The dynamic and static load ratings are given here. You can see the dynamic load rating, usually denoted by the variable C, is 400 pounds, while the static load rating C naught is 180 pounds. The expected lifetime of the bearing is most nearly. So we're looking for the life of that bearing measured in revolutions. Okay, so this problem is all about bearings, and I'm going to show you guys how to deal with this section and navigate some of those equations. So the first thing that we're going to do is we're going to head straight into the FE reference manual. Okay, so we have the FE reference manual pulled up over here in the section on bearings on page 434 of the reference manual version 10.4. You can see that the first equation over here is a relationship between load rating and life and applied load, right? So this is really the equation that we're going to be using. We're using a ball bearing here, so A is going to be equal to 3. If we go ahead and solve for the life here, L, That's going to be equal to the ratio of the load rating to the applied load raised to the third power, right? So we just kind of shifted over the 1 over a, it became instead of a 1/3, it became a third power there. So this is the main equation that we're going to be using, where L is the life measured in millions of revolutions. So that's that term on the left. That's what we're looking for. C is the dynamic load rating, and that is basically related to fatigue, right? So we want to use that in relation to the life that we're going to get. And then the last one is the design load. That is P, and that is just for the radial load. You see it says design radial load, but we're given both a radial and a thrust load. You can see I have it over here to the right. Wrote down some of our givens here. So what we're going to need to do is convert both our radial and thrust load or axial load into an equivalent radial load, and that procedure is detailed below. So we're going to walk through that process here. Now, in order to get an equivalent radial load, we're going to need to do this stuff over here. Now we know that in the case for us, what we have is the inner ring is rotating and the outer ring is fixed. So we understand that V is going to be equal to 1 here. The next thing is we have to check a condition over here where the ratio of FA over VFR has to be greater than E. And if that's true, we have X and Y given over here. And the X and Y is going to be used to get our equivalent radial load. But if that condition is not true, then we're going to have to use X equal to 1 and Y equal to 0. So that's the condition that we're going to be checking. FA over VFR, that's just equal to, FA was 40. We can see it above here. Pull up a little bit. Okay. FA is 40, V is 1 since the inner ring is rotating. The radial load is 120, so this is just 1/3. We have to check and see if that's greater than this term E here, which is this over here, 0.513. The axial load is 40. The static load rating, C naught, is 180 pounds, raised to the 0.236. So we have, that's equal to around 0.3597, and that is not, our third is not greater than 0.3597. So this condition is not true. That means that X is going to be equal to 1 and Y is going to be equal to 0. If we plug into our equivalent radial load up here, with X equal to 1, we know that V is equal to 1 as well, and the radial load was 120 pounds. Y is 0. So the axial load, which is 40 pounds, didn't have any contribution here. That's just going to drop off. The equivalent load is just 120 pounds here. Now that we know that, we can go in and plug into our equation up here. C is going to be the dynamic load rating, the one that's associated with fatigue. That's going to be 400 divided by our equivalent radial load, which was 120 pounds, cubed. 400 over 120 cubed is going to be equal to 37.04, and it's measured in millions of revolutions. So I'm just going to multiply this by 10 to the 6 and put 8 revolutions here. That corresponds to answer choice C here. So let's go ahead and move on to the next problem. In this problem here, we have a 22,000 kilogram fire truck and it's lifted by 4 identical screw jacks. Each has a 2-start square thread with a 48 millimeter major diameter and a 42 millimeter minor diameter. So let's go ahead and put down some of these things. We understand that the total mass is 22,000 kilograms and it's lifted by 4 identical screw jacks. That means that each one is really going to be lifting a quarter of that mass. So what I'm going to do is take that 22,000 and multiply by gravity, which is 9.81. The weight is equal to mg, but the load that's applied is equal to the weight divided by 4. So that is equal to 22,000 times 9.81 over 4. And that is equal to 53,955 newtons. We have a 2-start, so it is a 2-start thread, and that's important for finding out how much lead you have. And the lead is related to the pitch. That is just the number of starts multiplied by the pitch. Okay, so we're given a major diameter here equal to 48 millimeters and a minor diameter equal to 42 millimeters, and those aren't really important, but they can be used to find an important parameter we use for dealing with power screws. That is the mean diameter. So d sub m, that's equal to 45 millimeters. That is just the mean of 48 plus 42 over 2. Okay, and we also know that we have 4 threads per centimeter, and that is just given a value of threads per centimeter. Usually in the English system, we do like threads per inch. If you take the reciprocal of that, what you can find out is the pitch. So 4 threads per centimeter, or we could say a quarter. So I took the reciprocal of that, centimeters per thread. Okay, so this is really the pitch here. A collar of 30 millimeter radius, so the radius of that collar is 30 millimeters, is included with a friction coefficient mu equal to 0.2 at both the threads and the collar, so they have equal friction values. The torque required to raise the load is most nearly, so that is T sub R is what we're looking for. So this problem is really focused on the idea of power screws, and again, we're going to be looking inside of the FE reference manual here and seeing how we can use some of our inputs to find out the torque required to raise the load. All right, so on page 435 of the FE reference manual, version 410, you can see there is some information on power screws, and that's what we have in our scenario. So that is the square thread power screw, and you can see the torque required to raise the load. This is the relevant equation that we have. I wrote down some of our givens on the right side, and the first thing that I want to discuss, the little kind of trick in this problem, is that the pitch, right, the given pitch of a quarter centimeters per thread, we got that by taking the reciprocal of the amount of threads per centimeter. That is equal to 2.5 millimeters per thread, and that would be equal to the lead if if we had a single start sequence. Now the pitch is kind of a measurement between each adjacent thread, and what you can see is that the distance is equal to 2.5 millimeters per thread. If it was a single start sequence, then the lead, or the amount that you advance when you rotate the power screw by one rotation, would be equal to the pitch. But we have a double star sequence, so that means we're going to have to double the pitch to get the lead. So that's the first thing that we're going to do. The lead, L, is equal to double the pitch in our case, and again, that's because we had a 2-start sequence. So it's equal to 5 millimeters per thread. And we pretty much have everything that we need. We have the mean thread diameter here. We have the collar diameter. We have the friction coefficient, the load that we have over here. Let me erase this P. I'll just call it F here, like they do in the reference manual. We're lifting a quarter of that load, so let's go ahead and plug into T sub R, the torque required to raise the load. F was 53,955 newtons. D sub M is 45 millimeters. And we're going to divide that by 2. We're going to plug into the lead equation, which is 5 plus pi times 0.2 multiplied by the mean diameter. That was equal to 45 millimeters divided by pi times 45 minus 0.2 times the lead was 5. So this is the first portion, but we additionally have a collar here, so we're going to have to account for that second term. The force was 53,955. Mu is 0.2. The collar diameter, we were given the radius. We just doubled that to get the diameter, was 60 divided by 2. And the result of this calculation is equal to, I got 611,499, and that is in Newton millimeters, since all our dimensions were in millimeters. If we convert that to Newton meters, it's around 611 and a half Newton meters. Let's go ahead and check the answer choices to see what that corresponds to. That corresponds to answer choice D over here. Let's go ahead and move on to the next problem. In this problem here, we have a symmetric bolt group configuration, and it's made up of three 13 millimeter diameter bolts. So the diameter of those bolts are 13 millimeters, and that's shown above. The bottom bolt is enclosed in a purple box. The magnitude of the total shearing force on the bottom bolt is most nearly. So we're looking for the total force. I'm going to call that F3. So I'm going to label this bolt 1, bolt 2, and this one will be bolt 3. We're looking for the total shearing force on that bottom bolt. And it really has two contributions here. There is a primary shear, F3 prime, and there is a secondary shear, F3 double prime. Now the primary shear is usually a lot easier to calculate, and it's just the total force divided by the number of bolts. So the assumption there is that each bolt is going to carry the same amount of load. It's just going to be distributed evenly between each of those bolts. The F3 prime, or the primary shear, is just equal to 40 divided by the number of bolts. That's 3 bolts. That's going to be measured in kilonewtons. Now the secondary shear is a little more involved, and all we have to do there is determine if we have eccentricity in our system, or a distance between our centroid, the centroid of the bolt group, and the applied load. And in this case, it should be kind of intuitive that there is some eccentricity present. If we were to find the centroid of these 3 bolts, we would be kind of within the triangle that's created by these 3 bolts. And you can see our 40 kilonewtons on the outside. So we're definitely going to get some secondary shear. So our first thing is going to be to establish the centroid of our bolt group. And we have to choose a reference axis here. So I'm going to choose my reference axis to be, to simplify some of my calculations here. I'm going to call this my reference axis. And all we do is think about the idea of equivalent systems, which is supremely important in statics. And you can see it coming up again here in the mechanical design section. And what we verbally say is that the moment produced by these 3 areas is exactly the same as the total area placed at a specific point. The moment produced by these 3 areas, so triple the area placed at a special distance away. The total area placed at a distance away produces a certain moment. That must be equal to the moment produced by each one of the individual areas. A times y1 plus A times y2 plus A times y3. And of course, they all have the same areas because they have the same diameter. So you can see that the area terms are going to cancel out. And you also see that y1 and y2 are both going to be equal to 0 since they're aligned with our reference axis and there's no distance relative to that reference axis. So this term is going to be 0 as well as this term. If we solve for the y bar, what we're going to get is the ratio of y3, that's the distance from our reference axis to the third bolt, and you can see it's given as 70 millimeters divided by 3. So we have what the centroid of our bolt group configuration is. And if we kind of sketch it over here, it's closer to the upper 2 bolts, and it's just a third of 70 over here. This distance is 70 over 3, such that this distance, if it was a complement, it would be 2/3 of 70. So that when you add them both together, you get 70. Okay, so now that we understand the bolt group centroid, what we're going to do is establish an equivalent system where we place our actual load at the centroid of the distribution, and we see what kind of concentrated moment is going to come with translating that force. So if you kind of think in your mind of the equivalent system that we would need to create, we need the moment produced by the original system equal to the moment produced by the new system that we're going to create, where this 40 kilonewtons is going to be placed at the centroid of the distribution. Now, the total load must be the same. The sum of the forces have to be the same. The sum of the moments have to be the same in both of the systems. The sum of the forces has to be the same, so it makes sense that when we place that load, it's just going to be the 40 kilonewtons right there at the centroid, and we're going to get rid of this, pretend that's not there, and the moment produced has to be the same in both of the cases. Now, the moment produced by the first system, the original system where the 40 kilonewtons is all the way at the bottom of the flange, if we took a moment about the centroid, all we would do is take 40, which is the load, multiplied by the distance, that is this distance right here, 2/3 of 70 plus 15. That value comes out to be 61.667. If I multiply that by 40, I get a moments equal to 2466.67. That is kilonewtons millimeter. That's the moment produced in the first system, and it is counterclockwise. Now, if we want to establish an equivalent system in the second case, we need to place a concentrated moment at the centroid. Its magnitude has to be equal to 2466.67 kilonewton millimeters, and that's because our force placed at the centroid can't produce any moment, so we need that concentrated moment to produce everything that would have been produced in the first system. So now that we have our concentrated moments, we're able to find out what our secondary shear contribution is going to be. If you think back to mechanics of materials, we had this equation that the shearing stress tau is equal to TR over J, the torque, the radius divided by the polar moment of inertia. And if you think back to the definition of the polar moment of inertia that we discussed, I think it was in the first or second problem here. The polar moment of inertia J is equal to the integral of r squared dA. And for these three discrete points, what we can see is that that would just reduce to area multiplied by r1 squared plus r2 squared plus r3 squared. Right, we kind of add a contribution, area times r squared, for each one of those terms. So this term, if we wanted to write the shearing force as just a force or a secondary force divided by an area, and you could see that on the right hand side we would have the torque multiplied by the radius to that specific bolt divided by essentially area times the summation of r squared. You can see that the areas will cancel out here, and what we'll be left with is that the secondary shearing contribution is just equal to the torque multiplied by the radius to that specific bolt, r sub I, divided by the summation of r sub I squared. Not r sub I squared, just the summation of all of those kind of radial distances that exist inside of our bolt group here. Okay, so that equation, of course, is in the FE reference manual. We're going to go through where you can find that, but just to give you some intuition of where that equation comes from, I just wanted to go through that little exercise there. So if we're looking for the secondary shear that is present inside of that third bolt, we understand that the torque is equal to 2466.67 kilonewton millimeter. I'm not going to write the units because it's going to get a little crowded. The distance from the centroid to that third bolt is just this distance right here. 2/3 of 70, right? That's this distance. 2/3 of 70. And then the summation of r sub I squared. So I know that one of the distances is going to be equal to 2/3 of 70, and that is kind of our distance of interest above. And we're additionally going to add the distance right here, which is the same to the first or second one. It is just this kind of vertical distance, that is 70 over 3 squared, plus this horizontal distance, and that's just going to be kind of half of 100 or 50 millimeters here. such that we end up with this triangle where we have 70 over 3, 50, and we're looking for this radius right here, right? So 70 over 3 squared plus 50 squared, and that's going to be equal to our r squared value, right? And that's what we're looking for. We're summation of r squared here, so no square root necessary. So we accounted for one of the distances there, but remember that that distance is going to be equivalent for bolt 2 and bolt 1. So I'm going to double this distance over here. Now I'm going to plug into that calculation and let's see what we end up getting for the secondary shear contribution. All right, so I end up getting 13.925 kilonewtons. Okay, so we understand that our secondary shear is 13.925 kilonewtons. Our primary shear was just that 40 over 3 contribution. And in order to add the primary and secondary shear, we do so vectorially, right? So I should have put a vector symbol here on the primary and secondary shear because our total force is going to be the vector sum of primary and secondary. The primary shear is just going to be in the same direction of our direct shear. So that is going to be looking like this for bolt 3. And the secondary shear is determined by connecting a line from the centroid to the bolt. So if we draw that in red so it's a bit more clear. Let's say we're looking at bolt 2. As we connect that line, we just make a 90-degree angle like this. This would be the direction of the secondary shear for that second group, or that second bolt. This would be it for the first bolt, and this would be it for the third bolt. So what you could see here is the problem is a bit simplified because our primary and secondary shear are pointing in the same direction. When two vectors point in the same direction, their addition is the same thing as their vector addition. So all we have to do here is add together 40 over 3 plus 13.925. And the result of that is equal to 27.3, approximately 27.3 kilonewtons. So that corresponds to answer choice D. Now I'm going to check inside the reference manual with you guys to show you where you can find some of this information. And yeah, let's go ahead and finish up this problem. On page 439 of the reference manual here, you can see that we have some mention of fastener groups and shears, or bolt groups and shears, and that's the problem that we were dealing with. You can see we have a schematic here where they're trying to depict the primary and secondary shear. And one of the hardest part about these kind of problems is really picturing that secondary shear. All we do is connect a line from the centroid to the bolt of interest and just draw perpendicularly and aligned with the direction of the concentrated moment, the secondary shearing force, and that's an important concept to remember. So it could come from eccentricity or it could be just applied on the bolt group. And that's how we kind of determine the secondary shear. And the first part of the problem was really determining the location of the bolt group centroid. And it just came from kind of statics when we were finding centroid of different shapes, pretty similar to how we find the centroid of the bolt groups. Now, some people get a little bit confused on why we're taking moment of areas. And because this thing is constant in the thickness, because density is constant in the flange, the thickness of each one of these area contributions is constant. Once we take out a density and a thickness term, all we're left with is density times thickness times area times gravity. That's going to be the weight contribution. Now, because the thickness and the gravity and the density are all constants throughout this entire equation, we end up removing all of those and looks like we're taking moments of areas, but really we're still doing the same thing we have been. We're taking moment of forces, just kind of in a simplified format. Okay, so the next thing is that they mention the idea of direct shear or primary shear, and they also mention the secondary shear over here, where we have that equation that looks just like that torsion equation, right? T r sub I over that j term, and the areas end up canceling out. We just end up with the summation of r squared here. Okay, so let's go ahead and move on to the next problem. In this problem here, we have an hydraulic cylinder with an internal diameter of 230 millimeters. So that means that the inner diameter is 230 millimeters and a rod diameter equal to 80 millimeters. It operates at a pressure of 2.8 megapascals. We're given the rod length. It's 1.2 meters and there's no leakage at the seals. What is the difference between the push force and the pull force? Okay, so I think it's important to understand for this problem the geometry of a hydraulic cylinder here. So you can see there is a piston side. That's the side which is able to take advantage of the full area, right? So that would be pi multiplied by d sub I squared over 4. And there's also a rod side, right? And you could see that we don't have the entire area. It's pi over 4. This one will be d sub I squared minus the rod area, right? So really, if we want to understand the difference between the pull and push force, what we're going to want to do is the upper area will produce a force. We'll take a pressure, multiply it by that area. The lower area would also produce a force, pressure times that area. So really, if we just take the difference of those two areas, we can find the net force difference. So all we're going to do is the force. Pressure is just a force per unit area, or a force is a pressure times an area. And if we want the change in force, all we're going to do is the pressure times the change in area. Change in force is equal to pressure times the difference between these two areas. Right? The only difference between them is the d sub I term, so these are going to cancel out. And we're going to be left with a pressure times pi d sub r squared over 4. You see that minus kind of distributes here. That makes sense, right? The only difference between the upper and lower area is that rod area. We go ahead and plug into this equation here. Pressure was 2.8 megapascals, or a Newton per millimeter squared is a megapascal. We're going to multiply that by pi over 4, multiply by d sub r, that was 80 squared. And this is millimeters squared. You can see the millimeters end up canceling. We'll get a result in newtons of 14,074 newtons. And that's just equal to 14.074 kilonewtons. Okay, so that's answer choice D. So I wanted to do this problem because I think it's important to understand the geometry of hydraulic cylinders. And you could see it kind of tested this section over here on hydraulics. This is some easy points for you to get, so make sure you know how to do a problem like this. All right, let's move on to the next one. A gear train made up of 4 gears is made to transmit 15 horsepower at 1800 RPM. So the power that this gear train has to transmit is 15 horsepower, and the angular speed of the first gear is 1800 RPM. The number of teeth on that first gear is 24 teeth. It meshes with a 48 tooth gear, so that means that the second gear has 48 teeth on the same shaft as a 36 tooth gear. So the number of teeth on the third gear is equal to 36 teeth. And these two are on the same shaft, so that means the second and third gear are spinning with the same speed. The third gear is driving a 72 tooth output gear. So the number of teeth on the fourth gear is 72 teeth. The output torque is most nearly, so we're looking for the torque of the fourth gear. For gear trains, there's this important concept referred to as the gear ratio. And the gear ratio really relates angular speed, but its reciprocal could be used to relate output torque to input torque. The output torque is the torque associated with the fourth gear in our system. The input torque is the torque associated with the first gear in our system, and that's equal to the reciprocal of the gear ratio, where the gear ratio is really a ratio of the output angular speed to the input angular speed. And there's a pretty standard process to be able to find the gear ratio. So let's assume that we can find the gear ratio. If we knew what the torque of the first gear was, then we can use that torque of the first gear to be able to find the output torque or the torque of the fourth gear. Recall that power is just equal to the product of torque times angular speed. And we're not given any losses in the system, so we have to assume that conservation of energy is applicable. The power associated with the first gear is equal to that of the second gear, third gear, and fourth gear. They all have the same power, but their angular speed is constantly changing, so their torque must be constantly changing to keep the power exactly the same. What that means is that if we understand the power of the first gear, and we also understand and we're given the angular speed of the first gear, we can use that to find the torque of the first gear. Torque of the first gear is just going to be equal to the ratio of the power given to the angular speed of the first gear. We can use that torque in our equation below, along with the gear ratio, to find the output torque of the system. So it all really goes back to finding this gear ratio. Now that we have a plan, let's go ahead and execute on that plan. You can see I drew our gear configuration over here, where I'm really drawing the pitch circles associated with each gear. And the pitch circle is really the pitch radius is really a representation of the average radial location of the contact point. So when gear 1 and gear 2 are meshing together, their contact point will travel along a line. The average radial location of that line is used to determine the pitch radius, and double the pitch radius, you get the pitch diameter. And we can use that diameter to draw circles, right? And that's what we're drawing here. So it represents the average contact point, and the pitch radius, the pitch diameter, these are used in all of our angular speed, our torque calculations, right? So it's super important concept here. Gear 1 meshes with gear 2, and gear 2 and 3 share the same shaft. And finally, we mesh with a fourth gear, and that's the output. We're looking for the ratio of the output to the input angular speed, and we'll take that reciprocal to find the ratio between the output torque to the input torque. So firstly, the output angular speed, omega 4, to the input angular speed, omega 1. There's a super simple way to find this. All we do is take the product of the number of teeth of the driving gears to the number of teeth of the driven gears. So let's focus on the driving gears first. The number of teeth of the driving gears, gear 1 is driving gear number 2. Gear 3 is driving gear number 4. Those are the driving gears. The driven gears are the ones being driven by the driving gears. So gear 2 and gear 4. And we can plug in over here. The number of teeth of the first gear is 24. The number of teeth of the third gear is 36. Number of teeth of the second gear is 48. And the number of teeth of the fourth gear is 72. 24 over 48 is a half. 36 over 72 is a half. A half times a half is just a quarter. And we can take the reciprocal of that gear ratio and find that the relationship between the output torque and the input torque is just 4. So we're scaling up the torque by 4, and we're scaling down the angular speed by 4. Okay, so that's the easy way to find the gear ratio, but the more intuitive way is when we think about what's going on at the contact point. Now notice at the contact points, gear 1 and gear 2 are going to be touching, and because they're touching, they have to have exactly the same linear speed at the contact point. What that means is that when something is traveling with circular motion, we know that we can find the linear speed associated with that circular motion by taking the product of the radius of curvature, which is just the pitch radius in our case, multiplied by the angular speed. That's the angular speed of the first gear. This is representing the linear speed of the first gear at the contact point. That must be equal to the linear speed of the contact point for the second gear. That's just R2 omega 2. such that if we took the ratio of the output to the input, or omega 2 over omega 1 for just a simple two gear system, all we would end up doing is taking the ratio of R1 to R2. Okay, so that is the ratio of pitch radii. That's also equivalent to the ratio of pitch diameters and also equivalent to the ratio of the number of teeth. All of these things are related via constants, and when you multiply the top and bottom by the same constant, they end up just crossing out. So that's why this relationship is true. This is true for angular speed, and for force, there's also a relationship at the contact point, right? When two things are meshing together, they will have an equal and opposite force. That's Newton's third law. So we say that the force at the contact point for one is equal to force at the contact point for two. And remember that torque or moment is just equal to the force times the distance, such that if the forces are equal, this relationship has to be true. We can solve for the ratio of the output torque to the input torque, and what we end up getting is R2 over R1. Notice that's just a reciprocal of what we saw for the angular speed relationship. This is over here, right? So the angular speed and the torque, their ratios are related via reciprocals. And we could travel down the gear system and be able to find the gear ratio like that, or we can do it using the idea of driven and driving gears. Just to show you an example of how that will work, if we have, if we're looking for the angular speed of 4, we can start off at the first gear, right? We know that if we take the ratio of the number of teeth of the first gear to the number of teeth of the second gear, and we multiply that by the angular speed of 1, what we end up getting is the angular speed of 2, right? The input number of teeth to the output number of teeth multiplied by the input angular speed is equal to the angular speed of 2. And if the angular speed of 2 is equal to the angular speed of 3, this is essentially this and this. The product is essentially the angular speed of gear 3. If we take the input N3 over N4, multiply that by our previous product, then what we're going to get is the angular speed of 4. So we can do it either way. It's a little bit more simple to think about it in terms of driving and driven gears. Now that we know that the reciprocal of the gear ratio is equal to 4, we can plug into our relationship over here, where the torque of 4 is just equal to 4 times the torque of 1. And we discussed before that the torque is just the ratio of the power that's constant throughout the system divided by the angular speed. Torque of the first gear is the ratio of the power to the angular speed of the first gear. If we plug in 4 times the power, we know the power is 15 here. The angular speed is 1800, and there's definitely going to be some unit conversions over here. So we have horsepower divided by rotation per minute. Now I recommend that you memorize this conversion that I'm going to show right now. There is 550 foot-pound force per second contained in a single horsepower. The horsepower ends up canceling out. Now, if you don't want to memorize this, you can check inside the FE reference manual for this conversion constant, but I highly recommend you memorize this. It's super common in the English system to convert horsepower to foot-pound force per second and also BTU to foot-pound force, so that you don't have to look up those important constants that I mentioned just now. There is 778 foot-pound force in a single BTU. There is 7.49 gallons contained in a cubic foot. And the one that we mentioned below, 550 foot-pound force per second contained in a single horsepower. And I think these are the most important constants that you're going to have to know for the English system. Now let's go ahead and finish this up over here. We have the rotations per minute. We know that there's 2 pi radians per rotation. That's going to cancel out. And in 1 minute, there is 60 seconds. That's going to cancel out. we're finally going to be left with just foot-pound force. So this constant over here kind of reduces to 550 times 60 over 2 pi. If we go ahead and plug this into the calculator, what we end up getting is a torque of 4 is 175 foot-pound force. That is answer choice A to the left over here. Let's go ahead and check inside the FE reference manual. I'm going to show you where to find some of this information. This is on page 436 of the FE reference manual. You can see they talk about the gear ratio, the velocity ratio over here, the ratio of the output angular speed to the input angular speed, and it's just the product of the number of teeth on the driving gear to the number of teeth on the driven gear. You can see there's also a sign associated with it, and we didn't really discuss that in this problem, but I usually just like to think about it in terms of, drawing a couple of arrows here. So for our gear system, for instance, gear 1 was, let's say it was traveling clockwise. That would mean gear 2 travels counterclockwise. And if gear 2 is traveling counterclockwise, gear 3 would also be traveling counterclockwise. And what that would mean is that gear 4 would have to be traveling clockwise. So I usually just kind of think about it in terms of these arrows over here, and that's usually sufficient for the kind of gear systems that we're going to get on the FE exam. Okay, so that was one important concept that we used. Another one was power is equal to torque times angular speed. That's an important relationship that we use. And if we look over here, W sub T is the tangential or transmitted force. Another way to write this relationship is H, this relationship right here, H divided by R omega, right? Because the D over 2 is just a radius. And what we see is that the tangential force times the radius is just a torque, right? That's equal to the ratio of the power, H divided by the angular speed, or the power is equal to torque times omega. So that's also kind of given in the FE reference manual. Let's go ahead and move on to the next problem. A 3/4 inch 10, that's 3/4 inch diameter and 10 threads per inch, UNC steel bolt. UNC, that means coarse thread. If it was UNF, that would mean fine thread. Steel bolt is used to clamp steel members in a joint. The bolt is tightened to a torque of 250 foot-pounds. So we know that the tightening torque is 250 foot-pounds, and I know torque, that must be a force. A torque is a Newton meter or a foot-pound force. After tightening, an external tensile load, I'll just call that load P, is equal to 5,000. It's a load, so that would mean pound force, is applied to the joint. The stiffness of the clamp members is assumed to be twice the stiffness of the bolt. So the stiffness of the member is twice the stiffness of the bolt. The resultant load carried by the bolt, so we're looking for the force in the bolt here, after the external load is applied is most nearly. You can see on the right hand side of the screen we have a bolted joint and there's a bolt, and as we tighten that nut, that bolt is going to be elongated. We can ideally think of that bolt as a spring that is being elongated, and as it's elongating, it's actually squishing the two members, right? And we could think of the members as a stiffer spring. It's twice as stiff for our problem. Then there is an externally applied load P that's applied on the joint. And once we think about it like this as a system of springs, it's kind of intuitive to understand that not all of the externally applied load is going to be going into the bolt. Some of it is going to be used to elongate the bolt as we pull the joint apart, and some of it is going to be used to reduce the compression in the members. The parameter that kind of contains this information is referred to as the joint coefficient. It's the ratio of the bolt stiffness divided by the total stiffness, or the sum of the bolt and the member stiffness. And in this problem, we know that the member stiffness is just twice the bolt stiffness. So I went ahead and made that substitution right here, such that the joint coefficient is just a third, right? All the bolt stiffnesses kind of cross out. We're just left with a third over here. And how do we find the load in the bolt? The load in the bolt is just equal to whatever is transmitted to it by the externally applied load. So it's the fraction of the externally applied load that goes into the bolt. That is the product of C, the joint coefficient, multiplied by the externally applied load, plus whatever load it had in it due to the tightening torque, right? As we twist the nut, right, we're going to elongate the bolt, and due to that initial deflection, due to the torque that's applied to the bolt initially, we'll have some initial load, and that is what we call the preload. There is a torque tension relationship that we can use to find the preload. We already have the joint coefficient and we have the externally applied load, so we should be able to solve this problem. Let's go ahead and check inside the FE reference manual to find that torque tension relationship. Okay, so we're on the FE reference manual here, page 437 of version 10.4. You can see that there's mention of joining methods, and that's really what this problem is about, or bolted joints. And for a threaded fastener, you can see that we have that same equation that we just spoke about with the joint coefficient multiplied by the externally applied load. That represents the portion, that represents the load that's going to be going into the bolt due to that externally applied load. And we also add the preload. Everything that doesn't go into the bolt is going to be going into the member. That's why you see this complement term over here for the member. And then the preload is compressive on the member. It's not tensile like it is on the bolt. Bolt is being stretched, members are being compressed. You can see they define the joint coefficient over here. And we also have an equation for the bolt stiffness. Not applicable for us in this problem, but it's really just a function of major diameter, tensile stress area, elastic modulus, and some other geometric parameter. So if you needed to find the bolt stiffness, you could definitely find it using this equation. And there is a equation for the member stiffness. If you remember, we had that bolted joint, kind of like this, and I had some lines drawn. And it's thought that the compression of the members is really following a pattern like this, such that anything outside the lines is not really feeling compression. Anything inside of the lines is being compressed. And this truncated cone kind of shape is referred to as a frustrum. And, we know that stiffness, K is equal to AE over L, but the area is constantly changing here. And what we end up doing to find the stiffness is we integrate along this changing area, and we end up with this really long formula, and they reduce it to be this kind of exponential relationship over here, which is a little bit more simple. It's just a function of what material are you looking at and some constants. So we could definitely find that. If we needed to, it's not applicable for us. And there is a tightening torque relationship. This is what we were looking for. So we know that the torque, T, which is what was given in the problem, is equal to K. That is a torque coefficient, typically 0.2. And because it wasn't mentioned in the problem what it's supposed to be, I'm just going to use 0.2 there. 0.2 multiply by the preload, multiply by the bolt diameter. And that was given as 3/4 of an inch, such that the preload is equal to torque divided by 3/4 multiplied by 0.2. Our tightening torque was 250 foot-pound force. This is 3/4 of an inch. Foot-pound force. This one is inch. And there is 12 inches contained in a foot. So I end up getting that the preload is equal to 20,000 pounds. Okay. Let's go ahead and go back to the problem here. We understand that the preload, which came from that torque tension relationship here, that's equal to 20,000 pounds. The portion of the externally applied load that's going to go into the member that's categorized by the joint coefficient, that was 1/3, and the external load is 5,000. 20,000 plus 1/3 of 5,000 is 21,667 pounds. That is answer choice A here. Okay, so I want to give you guys some more intuition about these bolted joints. And we know how to apply the formulas, but really what I want to show you is something referred to as the joint diagram, and that'll give you some more intuition on this joint coefficient and how the entire system is working. Over here we have the joint diagram where we have the absolute value of the force, and that force could be used to represent the bolt or member force. And we also have the deflection over here. We understand from Hooke's law that force is equal to stiffness multiplied by deflection, or if we take the ratio of the force to the deflection, what we end up with is the stiffness. You can see I have two black lines over here. The first one is to represent the stiffness of the bolt, right, or the slope, which is just the ratio of the force to the deflection. And same thing for the member. I have a line associated with the stiffness of the member, and that's just twice the bolt stiffness. Okay, so the first thing that we're going to do is we're going to kind of sequentially step through the process of, firstly, we tighten that nut on the bolt. The bolt is going to stretch, the members are going to compress, and then we're going to apply the externally applied load and see what kind of effect we have on the bolt and member forces. Okay, so as we tighten the nut initially, what's going to happen is we're going to have a preload. So we start off right here, and if we travel to the right and we intersect the line that represents our bolt, you can see that we're going to have a positive deflection and we have a certain amount of force inside of the bolt, and that is equal but opposite to the amount of force in the member. So that's over here. And this makes sense, right? There's positive deflection associated with the bolt, it's being stretched, negative deflection with that of the member, right? It's being compressed. That's why it's to the left side of this plot over here. Okay, now as we apply the externally applied load, um, the bolt is going to deflect by some amount. It's going to be stretched by some amount. So I'm going to move to the right here, and I'm going to move the same amount to the right for the member. The same amount that I stretch the bolt is the same amount that I'm going to deflect the members. So I'm going to increase the tension of both of these. And what you see is that in the bolt, if we travel back up our line here, we have a small increase in the bolt force. We went from just having the preload to having a little bit more. And that little bit more over here is just the product of the joint coefficient multiplied by the externally applied load. And what about for the member? Now look what happened to the member experiencing that same positive deflection. We have much larger change inside of the member. So that is represented by 1 minus C, 1 minus the joint coefficient multiplied by the externally applied load. That is the portion of the externally applied load that is applied to the member. And this really comes down to the differing stiffness between the bolt and the member. You see a much larger change in the load of the member compared to the bolt because the member is much stiffer. I hope this gives you some more intuition about how bolted joints work. Let's go ahead and move on to the next problem. In this problem here, we have a spur gear, and that spur gear has 40 teeth. So the number of teeth is equal to 40. A pitch diameter equal to 200 millimeters. A pressure angle, that's Greek letter phi, equal to 25 degrees, and a face width, that is variable f, equal to 30 millimeters. The Lewis form factor, y is 0.35, and the load on the gear teeth, W is equal to 3,000 newtons. What is the stress on the gear teeth? Okay, so we have a spur gear here, and the spur gear bending stress, sigma, is governed by the following equation. W sub t, that's the tangential load on the gear teeth, multiplied by P, where P is actually the ratio of the number of teeth on that gear to the pitch diameter, divided by the face width, F, that's the thickness of the gear, and the Lewis form factor goes there. So if we kind of reduce this equation, W sub t n over d divided by f multiplied by y, W sub t, that's the tangential load on the gear. We can find that using the following equation. That is W cosine of 25 degrees. and that 25 degrees is just the pressure angle phi. Okay, I'm going to show you where you can find this in the reference manual, and then we're going to plug into this equation, and we should be okay. So right here on page 437 of the reference manual, you can see a spur gear tooth that's drawn over here. You can see the total load W, and you can see that that load is split into a radial component and a tangential component. That tangential component is what's producing power, and W cosine of phi is equal to the tangential component. We also have a schematic over here that F, this is into and out of the page. It's a little bit difficult to see here in 2D, but that represents the width of the gear, length of the gear, thickness of the gear, and the load, right? So it's kind of like a cantilevered beam with a load applied, and that's what we're going to use to find the bending stress. You can see Lewis's equation, that's over here, and this is essentially the equation that we're going to be plugging into. Okay, so let's go ahead and plug into this equation. So W sub T sigma is equal to W sub T. That's 3,000. That's going to be W multiplied by the cosine of 25 degrees. So this is W cosine of phi here. P. P is just the ratio of N, the number of teeth, 40 teeth here, divided by the pitch diameter D. That's 200 millimeters here. We'll write the units on the outside. Keep out the clutter. The face width, F, is equal to 30 millimeters. And the Lewis form factor, that's dimensionless, is 0.35. If we look at some of the units here, that 3,000 was measured in newtons. The ratio of the number of teeth to the pitch diameter, that is measured in, let's just do 1 over millimeters. That is divided by the face width is in millimeters, so this is Newton per millimeter squared. What we're going to end up getting here is Newton per millimeter squared. That is just a megapascal. So our result is going to be in megapascal when we plug into this. And the bending stress is 51.8 megapascals. That corresponds to answer choice B here. Let's go ahead and move on to the next problem. In this problem here, we have a pressure vessel with a radius R equal to 1.5 meters, a thickness T equal to 25 millimeters or 0.025 meters. The yield strength is equal to 250 megapascals. According to the maximum shear stress theory of failure, the maximum pressure which can be contained in the pressure vessel is most nearly. So we're looking for the pressure here. And this one is another problem on failure theories, but this time we also are bringing into the problem the idea of pressure vessels. Okay, so I could have chose to do a different failure criteria this time. Instead of maximum shear stress theory of failure or Tresca, we could have used von Mises, but I think that the maximum shear stress theory of failure does a great job in solidifying the fundamental idea behind failure theory, so I wanted to do another problem on this. It is all about the failure statement. Now, the failure statement says that the failure will occur in a body when the maximum shear stress in that body, so we're going to have to find the maximum shear stress here. The maximum shear stress in this body reaches that at failure in a simple tensile specimen. And thinking about a tensile specimen with a load P applied, if we cut the body and think about a stress element here, there'll be a uniaxial stress. That uniaxial stress is sigma x, and at failure, it will be equal to the yield strength. If we think about Moore's circle here for this uniaxial case, sigma and tau are the axes. If you plot the stresses on the y face, there's no normal stress and no shear stress. On the x face, there's just equal, the normal stress is equal to the yield strength. If we draw the circle here, Moore's circle, and we measure the radius or the y distance, this is going to be equal to the maximum shear stress. For the simple tensile specimen, at failure, that is equal to half of the yield strength. So now all we need to do is be able to find what the maximum shear stress in our actual case is. Now, for our body, it is a pressure vessel, and the first thing that we're going to do is check to see if we can use the thin wall assumption. That'll make the problem a little bit easier, right? We don't have to use bigger equations than we have to. And the check for that is to check to see if the ratio of the radius to the thickness is greater than 10. If it is, it's considered a thin wall pressure vessel. The radius is 1.5. The thickness is 0.025, same dimensions there, and that is actually equal to 60, and that's greater than 10, so we're good. We have a thin wall pressure vessel here, and that means that as we pressurize the cylinder here, we're going to have a hoop stress. That's the biggest stress that this thing is going to see, and it will be equal to P R over T, and there'll also be an axial stress. And at those spherical end caps, we'll have a stress equal to PR over 2T. Now we know that R over T was equal to 60 for our case, so the stress in the vertical direction is just equal to 60P, and in the horizontal direction it is equal to 30P. We're going to call this the X direction and the Y direction, and we're going to need to think about how does Moore's circle look for this case. So if we go ahead and go back to black, we put Moore's circle axes here of sigma and tau. What we're going to go ahead and do is plot on these set of axes the stresses that we have. And these are principal stresses or stresses in the absence of shear. So Moore's circle is super easy to construct for this case. We're going to start off over here with the stress on the X face. So there is 0 shear, but there is a normal stress equal to 30P. And on the Y face, there is a normal stress equal to 60P, 0 shear, principal stresses, of course. And if we go ahead and draw the Moore's circle, which is associated with the XY plane. So on the XY plane, as we rotate around the Z-axis for every angle theta, and we would plot out the stresses for each of those cases, we end up with this circle that comes from rotation around the Z-axis. This would be Moore's circle. One thing I want to note is that you can see that the angle between the stresses on the X face and the stresses on the Y face is 180 degrees on Moore's circle, but in real life it's 90 degrees here. And that's because all angles on Moore's circle are doubled. So actually, to get to the max shear stress, we would rotate around by 45 degrees in real life or 90 degrees on Moore's circle to reach this upper point. But this is actually not our maximum shear stress in the body. This is only considering the XY plane. There is additionally the XZ plane. And the stress on the Z direction is 0, right? If we go ahead and plot the Moore's circle for the XZ plane, now that circle is the same size as the one we just drew. And finally, there's one more circle that we can draw between the YZ on the YZ plane. And this is really what we're looking for, and we'll produce something called the maximum out of plane shear, tau max. And that is just equal to 60P over 2, which is just 30P. Okay, so if we think about the YZ plane, that's this vertical axis and the one out of the page. So technically, the maximum shear is experienced when we rotate around the x-axis. And if you can picture a kind of cut going through the cube, the stress element that would be created on that plane at 45 degrees, that's where we would see this maximum out of plane shear. So it's equal to 30P, and we know that we find the maximum shear stress in this body, it's equal to 30P. Failure is going to occur when we reach that at failure in a simple tensile specimen. That's equal to half of the yield strength. If we solve for P here, it's just the yield strength over 60. The yield strength is 250 megapascals divided by 60. What I get is that the pressure is equal to 4.167 megapascals. That is our answer there, and that is answer choice B over here on our left side. Let's go ahead and check inside the reference manual to see where we can find some of this important information that we can use to solve the problem. All right, so you can see the first reference over here on page 131 and 132 of the reference manual on cylindrical pressure vessels. And for our case, we had a simplification, so it's not quite these formulas over here. This is for when you have a thick wall pressure vessel or the thin wall assumption isn't satisfied. You can see the simplified case down here for when you have a thin wall pressure vessel and the condition is mentioned that uh, thickness of the thickness of the cylinder wall is about 1/10 or less of the inside radius. Thickness over radius is less than 1/10. Or if we wanted to rewrite this, we can do radius over thickness is greater than 10. So that is for the thin wall pressure vessel. You can see the tangential or hoop stress over here, and then the axial stress over here that we use to kind of populate our stress element for the pressure vessel. Okay, the next one is on page, well, I guess we did use Mohr circle in this problem, but technically we didn't really need to. But if you wanted to see the Mohr circle reference, that's on page 133 here. We constructed Mohr circle, and I think I put this reference in here because we wanted to talk about the maximum out of plane shear, and this is where that reference is. It's the first principal stress. That was our hoop stress for our case. That was the 6 CP minus sigma 3. The smallest principal stress was actually 0, right? There's 0 stress for the case of the stress on the Z face. That's because it's just exposed to the free surface. If we divide that by 2, we see that the maximum shear stress for our case was 30p, and we compared that to the yield strength over 2. Okay, so that was for discussing the idea of maximum out of plane shear. And the last one that we need to discuss is the idea of failure theories. And of course, there's for ductile materials on page 449 of the reference manual, there's mention of this maximum shear stress theory of failure. And, they say this, the failure statement, as well as the maximum shear in the body, first minus third principal stress, largest minus smallest principal stress over 2. That's exactly what we did. And we compared that to half of the yield strength or the shear stress at failure in a simple tensile specimen. Okay, let's go ahead and move on to the next problem. In this problem, we have a 4-inch long, half an inch wide, so the length is equal to 4 inches. The width is equal to half an inch, cantilevered rectangular leaf spring. Okay, so it's a cantilevered spring here. And it deflects a maximum amount equal to 1/10 of an inch when a load is applied at the tip. So this is kind of our scenario here. And the minimum deflection is equal to nothing, 0 inches. The steel has the properties shown above. So we have a bunch of different properties up there: yield, ultimate endurance limit, as well as the elastic modulus. With a factor of safety of 2, and using the modified Goodman approach, assume yield is safe, the required spring thickness for infinite life is most nearly. So we're looking for the thickness of this spring. And this problem is really about variable loading failure theories, right? So we have a load that's going to be changing. It's going from some maximum that produces the maximum deflection all the way to a minimum, and that minimum produces 0 deflection, so that minimum is 0. And there's the idea of deflection in this problem that's related to load, as well as we're analyzing a kind of cantilever beam over here, so it's related to the idea of stress analysis of machine elements. So we're hitting on all of these concepts over here. It's a good problem to bring together a lot of different things. I'd like to start off reviewing the idea of fatigue. And when we think about fatigue here, just the phenomenon is associated with variable loading. So if we draw a stress history here, let's say we have a 0 valued mean stress. The mean stress is equal to 0, and the alternating stress is less than the yield strength. We would have a plot kind of like this. It's a sinusoid representing the loading, and we call this loading scenario fully reversed. That's because the max and the min are equal but opposite here. And let's say that we have the case of, right, the alternating stress is less than the yield. What could happen in terms of fatigue is that you could still have failure even though you don't hit yield, right? And that's because of this kind of cyclic loading that it's experiencing. We would go and see what the number of cycles associated with this loading is, with this fully reversed loading is, looking at an SN diagram where we start off at the ultimate strength over here, and there's a slight dip going to 10 to the third cycles. There is a steeper slope associated with the life between 10 to the third and 10 to the sixth, and then there's a flat line that occurs for steel, referred to as the endurance limit. And the endurance limit is the stress below which you have infinite life, right? So if you're below this endurance limit, you can continually kind of cycle that part and you won't have failure. Okay, so this is the case for fully reverse loading, but if we observe our loading in our scenario, we have a max load, P max, and a min equal to 0. What that means is that if you sum the max and min and divide by 2 to find the average load or the mean load, you'll find that the mean load is just half of the max, right? And that is not 0. We don't have fully reverse loading, and that's where the concept of the modified Goodman theory comes in. It takes into account both the effects of mean stress as well as alternating stress. And if we kind of plot how the failure line looks for the modified Goodman approach, we plot the alternating stress and mean stress, and the original Goodman line, not the modified Goodman line, it considers what would happen if you have a zero valued mean stress. If you had a zero valued mean stress and just alternating stress, you would have non-infinite life if you went above the endurance limit. What about if you had a zero alternating stress and just mean stress? When would you have failure? You would have failure when you hit the ultimate strength of the material. So this line here represents the line associated with infinite life, and we call this line the Goodman line. Right, and this is just the equation of a line, so we can easily write this equation of a line, right? This is just some alternating stress over the endurance limit plus the mean stress over the ultimate strength, if that's equal to 1. So this is the equation of a line. Goodman connected these 2 points to form a line here, and that's his failure criteria. Now, this makes sense, right? If you have a zero valued mean stress, this term would disappear. And if you set your alternating stress equal to the endurance limit, you get 1. And if you had a zero valued alternating stress and you set your mean stress equal to the ultimate strength, you get 1. This is the equation of a line, and to incorporate the factor of safety, we simply scale up these stresses until we hit 1, right? Or we can move the n over like this, and this is essentially the Goodman line, right? And it was modified using a Langer line, which is just when we connect yield in terms of the alternating and mean stress, because we can still yield, right? I connect those 2 lines kind of like this, and if I kind of trace out the failure line that corresponds to the modified Goodman approach, it goes up to this point, and we also take into account yield. So it's kind of this line over here, and this red line is the modified Goodman. And of course, it's in equation form, so we're going to look at that, and really we just check the yield condition. That's how we take that into account. Now, in order to incorporate the yield criteria in equation form, all we do is we say that yield will occur when the maximum stress is equal to the yield strength, and if we wanted to incorporate a factor of safety, we can throw in N. It's the amount that you scale up the maximum stress until you hit the yield strength, and you can move it over if you want. So, and also I didn't really discuss, right, the idea of the failure envelope over here. Now, what does this plot really represent? if you have some combination of alternating and mean stress and it falls within the failure envelope defined by the modified Goodman line, since we're using that failure criteria, you're set to have infinite life. And if you fall outside, you'll have failure. Okay, so that's really what this is all about. First thing that we're going to start off with is looking to see in the reference manual where you could find the modified Goodman criteria. Okay, so let's go ahead and do that. All right, so here we have the modified Goodman criteria. So on page 449 of the reference manual here. And you can see that the one incorporated with the factor of safety is just this. And this is the equation that we're going to be using to incorporate our factor of safety of 2 here, right? That's for yield. And we don't really have to check yield in this problem. All we have to do is check for the fatigue condition. And that's because they said in the problem, assume yield is safe. Now, we'll still check the yield condition just for completeness here. But this is the equation that we want to apply. And we need to understand what is the alternating and mean stress. So there is a maximum stress that occurs at maximum deflection due to this maximum load that is a sigma max, and sigma min is equal to 0. If we go ahead and find what the mean stress is, it's just the max plus the min over 2, and having a min stress equal to 0 means this is just the max over 2. What about for the alternating stress? That is just the max minus the min over 2. And that's just the same thing, right? Max over 2. And if you think about the kind of stress history that will be associated with this, we'd have something like this. A sinusoid where the minimum stress is equal to 0 and the maximum stress is this peak over here. The alternating stress is represented by the distance between the mean stress and the max, right? And that's the alternating stress, and you can see they're both equal to the max over 2. If we substitute in the max over 2 into our Goodman criteria over here, what we see is that sigma max over 2 multiplied by 1 over the endurance limit plus 1 over the ultimate strength, that is equal to my 1 divided by my factor of safety. And the factor of safety for us is 2. You can see the 2's are going to end up canceling out such that the maximum stress is equal to just the inverse of this fraction over here. That is equal to 1 over 35 KSI. That's our endurance limit over here, plus our ultimate strength in the same location. Approximately, it's around 1 over 80 raised to the negative 1. And what this means for us is that the maximum stress, it has to be 24.348 KSI. So that's the maximum stress, and we're looking for the thickness in this problem. That's the maximum stress. Now, what is the maximum calculated stress for a cantilever with a tip load? If you think about it, right, there's really only going to be bending stress here, and the max bending stress would occur at the kind of upper surface. That's where the most tension is going to occur, and all the way at the fixed end. Sigma max is equal to MC over I. If you think about the section over here, we have a rectangle with a thickness T, and that's what we're looking for, and a width W. Now the moment at the fixed end is just the product of the applied tip load multiplied by the length. C is the distance from the neutral axis to the outer fibers. That is half of the thickness for our case, T over 2. And then there's an inertia term in the bottom. If we go ahead and solve this for the thickness, what we get is this is just the maximum stress multiplied by the moment of inertia multiplied by 2 divided by P times L. So this is our thickness that we're looking for, and we know what the maximum stress is according to the Goodman criteria. We don't know what the inertia is, and we don't know what the load is either. but we do understand what the deflection is, right? The deflection is just equal to 0.1 of an inch. So we know that there is a relationship between deflection and load that we can incorporate into this equation. So the first thing we're going to do is check in the reference manual to see where we can find that. On page 141 of the FE reference manual, you can see some of the deflection tables over here, and they'll give you the deflection load relationship right here. So we had a cantilever beam with a load applied at the tip that would correspond to this case over here with B equal to 0 and A equal to the length. Let's find what the maximum associated deflection will be. That is, if I substitute over here, what I get is a 2L for this term. The 2 and the 6 will cancel out. I'll get a third. So what I really have is PL cubed over 3EI. And there's a negative sign associated with that. I'm just going to leave off the negative sign. That's just associated with kind of what they're assuming their coordinate system is. This is our deflection equation over here. Let's go back to the problem. Delta is equal to PL cubed over 3EI. And if we just solve for the load, because what we want to do is substitute the load into this relationship right here, because we know what the deflection is, right? The load P is equal to 3EI delta over L cubed. If I plug that right in here, what am I going to end up getting for the thickness? Well, the first thing that we see is, and I'm going to write down the whole equation so we can see all the terms that cross out. Sigma max I2 divided by 3EI delta over the length cubed. And we take that multiplied by the length. So first thing I'm seeing here is we get an L squared in the denominator of the denominator. The inertia terms are going to go ahead and cross out. So we'll be left with the following here. 2 multiplied by L squared. 2 is taken into account. L squared is taken into account. The sigma max in the numerator divided by 3E delta. So what do we know inside of this equation? We know what the length is. That was equal to 4 inches. We know what the maximum stress is from the modified Goodman approach. That was 24.348 KSI. We know what the elastic module is. We know what the deflection is. Let's go ahead and plug into this equation. 2 multiplied by the length was equal to 4 inches. That's this term up here. And we also needed the elastic modulus. 2 times 4 squared multiplied by the maximum stress. If you could see it on the upper right over here. That's 24.348 KSI times inch squared. That's going to be KSI in the that's going to be kips in the numerator. In the denominator, we have a 3. 30 times 10 cubed KSI, and the deflection, the maximum deflection is 0.1 inch. So we have kip per inch in the denominator and kip in the numerator. We end up with a thickness in inches of around 0.087 inches, and that corresponds to answer choice A. Now, this problem was definitely a more difficult problem. We had a lot of different concepts that we brought together, things like fatigue. We talked about fully reverse loading, different failure criterias. We looked at beam deflections. And I think it's really the perfect way to stretch your capability and really test your understanding of a bunch of different concepts. On the FE exam, you're going to have difficult questions. And I recommend, if I saw this question on my FE exam, I would flag it, come back to it later. But in terms of your practice, I think this is perfect for being able to really put together multiple different concepts and get a nice review of all the different things that you could see on the FE exam. I hope you found it helpful. Let's go ahead and move on to the next problem. In this problem, we have a flange and it has a design diameter of 60 plus or minus 1 millimeter. So the diameter D is equal to 60 plus or minus 1 millimeter. Each day, 10 holes are measured for 7 days. The sample mean is 40% of the tolerance from the maximum material condition, or MMC, and within the limits. The average range is 40% of the tolerance for a Shewart X-bar control chart. The lower control limit is most nearly. So we're looking for the lower control limit, and that is based off of the average or X-bar chart over here. What is that going to be equal to? And we were given some information about the overall average, or X double bar. The average range is the sample mean is 40% of the tolerance from MMC and within limits. So 40% of the tolerance range is 0.4 multiplied by the overall tolerance range. The total range of variation that we could see in terms of the design is 2 millimeters, or 1 minus a negative 1. And we need to find out how that's going to interact with the MMC condition. So that is for the overall average. And what about for the average range? The average range is 40% of the tolerance here. So R bar is equal to 40% of the tolerance. That's just equal to 0.8 millimeters. So this problem is really about the idea of quality and reliability, as well as some GD&T concepts thrown in there. And if you're kind of struggling to visualize what the problem is asking, we really have a kind of chart here where each day would represent a single point. So we would have 7 days, 2, 3, 4, 5, 7 different days. And on each day, if this was an average chart, the 10 holes, or the 10 measurements that are taken, would be averaged and represent a single point on this plot. And you can do that for every single day, right? And not only will there be an average associated with each one of these points, there can also be a range, or the difference between the max and min, the difference between the max and min measurements. So each of these would have their associated range, and the R bar, right? That's just the average range for our entire data set. So that was given as 0.8. And X double bar, or the overall average of the entire data set, that's equal to 0.4 times 2 plus or minus the MMC condition. So that's kind of what the problem is asking, and it's focused on the lower control limit. So there's some bound down here called the lower control limit, and it's based on the average. And if we had a point below the lower control limit, we would say that something outside of kind of random variation would cause a data point to fall below that value. And there's also an upper control limit, so something outside of randomness is causing the a data point to fall above that specific limit, right? This would be the upper control limit. So we're trying to determine those limits in this problem. And the first thing that we're going to need to do is think about the idea of maximum material condition. And this is a very important distinction between if you're talking about an internal feature like a hole, or an external feature like a cylinder. And of course, we're talking about a hole in this case, but I'll discuss both cases here. Now, if we had a cylinder, the maximum material condition, or the most amount of material that could be used to that could be used that hole could measure, is 60 plus 1, or 61 millimeters. And that makes sense, right? The cylinder is as large as possible. The most amount of material is used for that cylinder. Now, what about for a hole? For the hole, it's a little bit different, right? If we're thinking about the maximum material condition for a hole, or the most amount of material used for a hole, it's when the hole is as small as possible. So that'll be 60 minus 1. That's 59 millimeters is actually the maximum material condition here. So that's the maximum material condition for a hole, and we don't have a cylinder in our case, right? We're measuring holes inside of a flange. So we have 59 millimeters here. We can plug that in up here, and we understand what the sign is going to be now. So X double bar is equal to 0.4 times 2, or 0.8, plus the MMC condition. I know it's plus because they said within the tolerance range. The sample mean is 40% of the tolerance from MMC and within limits. So that means within limits means between 59 and 61. So this is within limits. Okay, so we understand the X double bar value and the R bar value. And there are some statistical constants that are associated with finding things like the lower control limit. So let's go ahead into the FE reference manual and find those constants. So you can see on this page here, page 82 of the reference manual, under the section labeled statistical quality control, there is some information on constants associated with average and range charts. They define a mean for an individual data point. That's just the sum of all the measurements divided by the number of measurements. So that would be 10 for our case. Or you can take the average of each day, that's X bar 1, X bar 2, all the way up to 7 days for our case, and divide by 7. And that'll give you the overall average of the data set. That's what we have. We also were given R bar in terms of the MMC condition. That's just the average range of the entire data set. Okay, and if we want to find the lower control limit based off of the average, what we're going to need to do is find X double bar. We found that. R bar, we already have that. And what about A2? A2 is a constant from the table above, and it's based off of N, or its sample size per group. The sample size associated with each data point is 10. 10 holes are being measured in a flange, so the A2 value is 0.308. We're just going to plug into that lower control limit right there, and then we'll be able to solve this problem. So this is our formula over here, where X bar, that was equal to 59.8, that's X double bar, minus A2 was 0.308, multiplied by the range, and the range was 0.8. And if we plug into our calculator there, we'll get 59.5536. That corresponds to answer choice B here. I also have a schematic of this Shewart X-bar control chart that you can find below so that we can understand how this data looks when it's plotted. So I went ahead and plotted a kind of random set of data, and you can see that for each day, for each one of these days down here, I have a measurement that represents the average for that day. And you can see that, for instance, the average on the first day is actually above what I plotted as the upper control limit. So the average is above the upper control limit. There's something outside of just random variation that's causing that point to be above the upper control limit, and nothing is below the lower control limit. That's what we found in our problem. You can see here that I also plotted the design limits, 61 up here, and then 59 below here. Hope this schematic was useful for helping you kind of visualize what this problem is asking. Let's go ahead and move on.
Studying for the FE exam can feel overwhelming. There's too many topics and not enough time. And when you're pulling resources from all over, you have YouTube, textbooks, random notes, you waste hours dealing with different teaching styles, scattered methods, and constant friction that leads to wasting valuable study time. What if you had a proven system to focus on high weight sections, the fundamentals to help you build confidence, speed, and actually pass the FE exam? That's why I created FE Interactive, a super affordable FE mechanical prep software that puts everything you need in one place, eliminating that friction and letting you maximize your time actually studying. We give you access to multiple different sections like the review and improve section, as well as a tips and tricks section to help you use your calculator more efficiently. You can take time practice exams and even view video resources if you're a more visual learner like I am. You can see full reviews, or you can access specific questions with video solutions. Some of these sections are also tied together with our analytics page. Inside the analytics page, you can see data from the improve and review section, as well as, most importantly, the exam section, where you can view data from each of the exams that you've taken. You'll be returned a scorecard once you click on that specific data point, where you can view your performance in each subject, as well as a specific solution manual here. And you can access those typed and handwritten solutions. All of the data is tied together using an overall data point over here that gives you aggregated data. You can view it here or inside of our passing roadmap section. And in this section, I designed it to give you more structure to your studying, to help you make data-driven decisions on what you should be doing next to help you pass the exam as fast as possible. FE Interactive is a fraction of the price of any other paid resource out there. And right now, it's only $20 for 2 full months of access, since we're a new platform and we're focused on improving and getting feedback from students like you.
It could be the reason that you pass on your next attempt, just like it has been for some of our users. Click on the top link in the description below to try FE Interactive for yourself. If you made it this far in the video, I just want to say thank you. And if you found this video helpful, there's a good chance that your classmates and coworkers would find it useful too. I'm a small channel and I'm trying to grow and would really appreciate if you could share the channel with them so that I could reach more people like you. Please leave a like and subscribe to see more content like this. Every few weeks, I'll be releasing a new review, so stay tuned for that. Again, thank you for watching. I'll see you in the next one. Goodbye.